Hey everyone, we're going to continue our discussion of periodic trends. And now that we have some idea of how the periodic table is laid out, we can start using the periodic table as a tool to predict chemical reactions. And the next periodic trend we're going to talk about is called ionization energy. And this has to do directly with certain kinds of chemical reactions. Ionization energy is the energy required to remove an electron from an atom in the gaseous state. So, to start talking about chemical reactions, we need to have an understanding that sometimes it is the gain and loss of electrons that is what is responsible for a chemical reaction. Other times, it's the sharing of electrons that's responsible for a chemical reaction. In this case, obviously, we're talking about the loss of an electron and how much energy it takes to remove an electron from an atom depends on a few things. One of the things is the focus on the strength of the attraction between the positively charged nucleus and the negatively charged electrons. And so when you learned about atomic radius and ionic radius, we did a bit of discussion about how much charge is coming from the nucleus, how strongly can the nucleus attract the electrons, which are the opposite charge. And so we're going to rehash that idea. And also we're going to think about how the stronger the attraction is between the positives and negatives, the more energy it takes to remove an electron from that particular atom. So if we look at a table, or rather a graph of the ionization energies, we will see that up here, well, first we have a jaggedy sort of curve here, but at the very top we have the noble gases. Now, if you think about what you know about noble gases, hopefully what comes to mind is that they're non-reactive. And so now when we're talking about the energy needed to remove an electron from an atom, it shouldn't be surprising that here on our y-axis, where we're looking at that amount of ionization energy, we see that the noble gases are way up on that y-axis. It takes a lot of energy to remove an electron from a noble gas atom. And so that hopefully will make sense to you when you consider that we know that the noble gases are non-reactive. On the other hand, if we look at the very bottom of these curves, right across the bottom, the atoms that require the least amount of energy to remove an electron are the atoms in the alkali metals. And so they are at the extreme opposite end of the periodic table from the noble gases, and they have the extreme opposite ionization energy. It takes the lowest amount of energy to remove an electron from those atoms. So let's talk about why we see these sorts of things happening when it comes to atoms reacting and the removal of electrons. First, the trends are that the further down a column we go, the lower the ionization energy. So remember, we're talking about the energy needed to remove an electron. And as we go left to right, the further across a row, the higher the ionization energy, or the more energy it takes to remove electrons from those atoms far to the right, like noble gases. So the Y is going to take us back to the last video. So here we go. As we go down a column, atoms become larger, so the nucleus doesn't have as great an attraction for the electrons. That means it's easier to remove electrons. So I'm going to draw the same drawing that I did in our last video. If this is the first row of the periodic table, that means that atoms in that row have one energy level with electrons. In the second row of the periodic table, our atoms have two energy levels of electrons. Made that a little squiggly there, but you get the point. In our third row of the periodic table, our atoms have three energy levels of electrons, and so on. So remember, every row that we go down in a group, we get one more layer of electrons added to that atom. Because we have more electrons, that electron cloud is spread out to a larger and larger volume. The reason for that is, remember back to the last video, we talked about the repulsion between electrons. So more energy levels of electrons means more electrons. And the more electrons you have, the more they will repel one another. And so our electrons have to spread out further from the nucleus every step we go down in a group. In addition to that electron shielding, we also, remember, have the effect of the core electrons, the electrons on the inner part of the atom, blocking the valence electrons, or the outermost electrons, from feeling the pull of the nucleus. So when you put that all together, we have bigger atoms as we go down, 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 and the bigger our atoms are, that is due to more electron repulsion, and so the nucleus can't attract these electrons out here as tightly. So if they're not attracted well, you can remove them with less energy. It's easier to remove them. Now, going across a row, the atoms become smaller. So remember the reason for this. In the last video, we talked about the effective nuclear charge. So going across a row, our atoms of our elements all have the same amount of energy levels. So it's not like what we just discussed in columns. Because our atoms get another proton added to the nucleus each step that we go across the row, that means the effective nuclear charge increases. So the nucleus has more protons going across that row. The number of energy levels stays the same, but the increase in protons in the nucleus means that the nucleus has a greater attraction for electrons. So it's harder to remove an electron from a smaller atom, like those we see as we go to the right. That nucleus attracts the electron more, so it takes more energy to pull an electron away. Now, I want you to pause the video and take a look at these questions, give them an answer, and then come back and see how you did. Here we go. In our first question, we are comparing titanium, zirconium, and hafnium. And if you look at these elements, they are in the same column on the periodic table. So what has the highest ionization energy? Meaning, of those three, for which type of atom is it going to take the most energy to remove an electron? The answer here is titanium atoms. Titanium atoms are at the top of that column, which means that of the elements in that column, it has the smallest atoms with the least number of energy levels in its electron cloud. So the nucleus of titanium atoms attract its electrons more closely, therefore it has a higher ionization energy. Number two, what has the lowest ionization energy of vanadium, niobium, and tantalum? Again, these are in the same column. They're in the column right next door to the ones from the first problem. This time, we're talking not about the highest, but the lowest ionization energy. So in other words, for which type of atom is it easiest to remove an electron? The answer here is tantalum, Ta. The reason for that is that tantalum has the most energy levels of those three kinds of atoms. It has more than the other two, so the nucleus with the protons is just physically further away from the valence electrons and the outer electrons. So to remove one of those electrons takes less energy. Number three, which actinide has the highest ionization energy? This is the very, very bottom row on the periodic table. And this time our answer is Lr, lawrencium. Lawrencium is the furthest to the right of that row of actinides, and therefore it has the smallest atoms. The protons in the nucleus attract the electrons more strongly in those atoms compared to the others. Therefore, it takes a lot of energy to remove an electron. Number four, which chalcogen has the lowest ionization energy? We haven't really talked about chalcogens, or that name, chalcogen, but chalcogen actually that word, refers to the group 16 elements. So you can write that in there for yourself if you were wondering what the heck that word meant. And so here, the lowest ionization energy in group 16 is LV, which is one of our newest elements. That has the biggest atoms, the least attraction between the nucleus and the electrons, so it takes not a whole lot of energy to remove an electron. Lastly, of AS, SE, and BR, these are in the same row together, and so AS, being the leftmost element there, has the biggest atoms of those three. Since it has the biggest atoms, that means there's less attraction between the nucleus and the electrons, so it takes less energy to pull an electron away. Now, similar to the idea of ionization energy is our last periodic trend that we're going to talk about, and this is electronegativity. Electronegativity is defined as the ability of an element to attract electrons to itself when it already is in a bond with another element. So, because of that, noble gases are not included in this trend. Remember, noble gases don't bond, so we aren't going to be referring to their electronegativity values, but all of the other elements are fair game. This trend is going to be very similar to the ionization energy trend in that the value of electronegativity is determined by the attraction between the positively charged protons in the nucleus and the negatively charged electrons in the electron cloud. Basically, again, same reasoning is going to apply. The stronger the attraction between that nucleus and the electrons, the more those electrons will stay attracted to that atom. And so that will affect our electronegativity values. We have a table here in the notes of the electronegativity values of a number, well, really, not all the elements on the periodic table, but quite a few of them. So if you take a look at this, you can see that fluorine up here in the upper right corner has the highest electronegativity value of any atom on the periodic table. And then they decrease as we go to the left, and they also decrease as we go down the column. So let's talk about why. So first, just stating the trends, the further down a column, the lower the electronegativity, or the lower the ability for an atom to attract new electrons to itself. And the further across a row, going from left to right, the higher the electronegativity value is. So as we go toward the right, the atoms of elements on the right of the periodic table are more likely, when they're already bonded, to attract new electrons to themselves. So now we need to think about the why. And the why is very similar reasoning to ionization energy. As we go down a column, the atoms become larger, so the nucleus doesn't have as great an attraction for the electrons. Therefore, if the nucleus is going to attract new electrons to itself, it's going to be more difficult for the nucleus to attract those new electrons. So same diagram I've been drawing. If we have elements in row 1, row 2, and row 3 of the periodic table, as we go down, we get a new energy level of electrons. So there's more electron shielding between the nucleus and the outer electrons, and therefore the nucleus can't attract these electrons as easily. So attracting new electrons is definitely harder for these bigger atoms. As we go across a row, the atoms become smaller. So the nucleus has a greater attraction for the electrons, and it's easier to attract new electrons into that atom. So again, pause the video, take a look at these 5 questions, give them an answer, and then come back and check to see how you do. Okay, let's take a look at your answers to see how you did. Which of iron, cobalt, and nickel have the highest electronegativity? If you look at the placement of these elements on the periodic table, they're in the same row, so they have the same number of electron energy levels, but nickel is furthest to the left, cobalt is furthest. One more time, iron is furthest to the left, cobalt is in the middle, nickel is furthest to the right. So therefore, nickel has the highest electronegativity. So nickel atoms of those three are more likely to attract new electrons into themselves because they're smaller atoms. So that means the nucleus has a greater charge for the electrons in nickel atoms. That has to do with the effective nuclear charge, more protons in the nucleus of nickel than in cobalt or iron. And so that greater effective nuclear charge means attracting new electrons into the atom is easier. Which has the lowest electronegativity, which is least of these three, least likely to attract a new electron into itself. So magnesium, calcium, and strontium are in the same column. Therefore, we're looking at how many energy levels these atoms have, and strontium has more energy levels than the other two. So attracting new electrons into a strontium atom is not going to happen as easily. The strontium nucleus is just farther away from its electrons because of all of those energy levels, so it has the least or the lowest electronegativity. Which series 6 element has the highest electronegativity? The answer to that is AT. So if we look at AT or astatine, it is the furthest right in series 6. Notice I didn't say radon, which is really the furthest right, because radon is a noble gas, and noble gases are not going to form bonds. So we're going one less than the noble gas, AT. AT has the smallest atoms because it has the greatest number of protons in its nucleus, greater effective nuclear charge, in other words, and so attracting new electrons is easiest for AT. Which halogen has the lowest electronegativity? Halogens are in group or column 17, and that halogen is TS. TS has the most energy levels. It's all the way at the bottom of the group of halogens. So the nucleus is very far away from those outer electrons. It has much lower charge for those electrons than the other atoms of the other elements in that column. And so TS has the lowest electronegativity, the least chance of attracting in new electrons. And lastly, which has the lowest of Zn, Ag, and Pt? These elements are in a diagonal, but Pt is the furthest down of the three on the periodic table, so that means it has the most energy levels of those three kinds of atoms, and it's also the furthest to the left. And remember, the further we go to the left, the larger the atoms are, because there is a less effective nuclear charge. So PT is the answer for number 5.